Hey, it's Tony from Adafruit, and in this video I'm going to look at how to use NeoPixels with CircuitPython. So CircuitPython is Adafruit's version of MicroPython, but it's focused more on beginners. And things have changed a little bit with CircuitPython in how the API is structured. So if you've tried to use NeoPixels, it might not have worked very well, or you probably ran into an error. And so I'll show you a quick little update to the NeoPixel library and just real quickly how to use that. And then I'll also show you something kind of cool, because in the context of using NeoPixels, I have a fun little project that I'm working on for the Emerald City or the Seattle Comic-Con. So I want to go and cosplay as Tony Stark, and he has the iconic arc reactor on his chest like this. Apparently it's like a little fusion reactor that powers an electromagnet that keeps a piece of shrapnel from killing him, apparently. So it's a little hardcore, but this is kind of cool. It's just a really iconic thing. Now I'm doing some neat animations with this. I guess the purists will say that the arc reactor doesn't flash like this, but I figured, you know, if I've got all these cool pixels, why not animate them and make them different colors and pulse and glow and things like that. So we'll look at how to build this thing, which I'll show you in a second here what this is. Actually, let me turn it off because it's a little bit bright. And uh-oh, there goes the cat. She might have some fun here. But this is basically a circuit playground. So this is the ATmega 32U4 version of Circuit Playground. This is the Circuit Playground you can buy in the Adafruit store right now. This one does not run CircuitPython. So I'll show you though. We've done a few little kind of don't ask, it's not out yet. Previews of it, the CircuitPython or the Circuit Playground board that runs CircuitPython, and that's using this processor, or the processor that's on this Feather. This is the Feather M0. This is the Ada Logger version, but it's the SAMD21 microprocessor. It's the processor that we've ported MicroPython to run against. So real nice, low cost, but high feature microprocessor. So we'll look at how to use the Circuit Playground version with that fancier microprocessor that can run CircuitPython, which is basically MicroPython, and we'll look at how to control the NeoPixels on it and build something potentially like this little arc reactor. And I'll show you this is actually more than just a Circuit Playground. So this is, this is your normal Circuit Playground right here, which has 10 NeoPixels. They're a little hard to see, but they go around in a ring all the way around this. And then I've augmented it with this. This is a ring of 24 NeoPixels. So you can get this in the shop. And then the cool thing is, this fits perfectly with a Circuit Playground in front of it. So you can see the Circuit Playground is 2 inches wide, and this NeoPixel ring, the inner diameter is 2.1 inches. So you've got a teeny little bit of play inside of there to connect these. And then this is cool. So it gives an extra ring of pixels. So you get 24 pixels on the outside and 10 pixels on the inside. Gives you a little bit more kind of pop or glow or a little more light with this. So as you saw, it's nice and shiny. So let's just kind of dive in. Like I said, I'm first going to start with how to control NeoPixels with CircuitPython. So this will be useful for anyone that wants to do a NeoPixel project, and eventually when we have the Circuit Playground board that runs CircuitPython, be very handy to see how to control the NeoPixels on there. And I'll show you how to use a quick little library update to use NeoPixels. And then we'll look at how to write some code to animate that outer ring of pixels and the inner ring of pixels. I don't think we'll build the full project. I don't think I have time for that in this video, but I'm sure in a later video we'll look at kind of the finished product when I get to it. So let's jump to the main view and we'll see. So right here, this is maybe the star of the show. This is a prototype version of the Circuit Playground with the SAMD21 processor, which can run CircuitPython. It's actually loaded with CircuitPython right now. So this is almost exactly the same as this Circuit Playground right here. This is the classic Circuit Playground, I guess I'd call it, which has the ATmega 32U4. But this one you can only program it with Arduino. You have to use that C-based Arduino language, and you can't really interactively program it. You don't have the Python REPL and things like that that you get with MicroPython and CircuitPython. But same features as far as what's on the board. So there are 10 NeoPixels on Circuit Playground. Same thing on the Express version. I think we're going to call this Circuit Playground Express. I'm not exactly sure. The names aren't kind of final yet. But the one difference is this board, like I said, has a bigger processor, the SAMD21. It's an ARM Cortex chip, more memory, more speed, just overall a little bit better chip. And it also has a little flash, serial SPI flash ROM on it, or EEPROM, which basically you can program the memory of that flash chip. And with CircuitPython and MicroPython, when you have a bit of memory like that, flash memory, you can make it look like a file system where you load your Python code. So I believe this board has a 2 megabit flash, but who knows, the final board will probably be a little bit different. But that means you can get a lot more space because the flash memory of the microprocessor is only about, I think, 256 kilobytes on the SAMD21. So that's pretty limited, and you want to use some of that space to store your MicroPython code, and then the rest of that space is for the MicroPython firmware. So there's a trade-off there of how much space you want for the firmware versus your code. Whereas when we have this little external SPI flash on here, we can make that SPI flash all for your Python code. So you can have all 2 megabytes or 2 megabits of that SPI flash just for Python code, like your libraries, your assets. You know, if you have like images or data files or things like that, it can all go onto that external memory. And then the memory of the CPU, that 256 kilobytes, can be dedicated completely to MicroPython or CircuitPython, which means you can add more to the firmware. So you can put in more modules, we can add more features to it, things like that, that'll make it easier to use and more powerful. So this is what we're going to do, and then I'll show real quickly. So this is, I actually built this in a video. I'll put, look in the link in the description below. I'll put a link to a video where I just did like a time lapse of building this, this Circuit Playground Arc Reactor. And as you saw before, when I plug in a battery, it just starts to light up and glow. So it kind of goes through like this kind of pulsing animation here like this. And it's a little bright. I mean, you can see here, this thing is, this is bright. But it's kind of cool. And it is neat when you put it underneath a shirt, you can actually see it through there. So it's, you know, gives you that cool kind of Iron Man look. So I think this will be really neat once I get it kind of working and in action. But all that this is, like I said, is just this ring of NeoPixels with Circuit Playground in the middle. And maybe in the future I'll do a video on this. I'll do a guide for sure that explains how I created this. But it's really as easy as you can see. I just soldered wires to, so there's the VBAT pin on Circuit Playground. That gives you the output of the battery that's plugged in, and you want to use that to power your NeoPixels because NeoPixels can pull a lot of power. So you don't want to use like the 3.3 volt power output because that goes through the regulator, which is limited to like 500 milliamps, something around that level, which is way too little for all of these NeoPixels. If they're lit up, they can pull quite a bit of current. So you want to use the VBAT pin as your power source. So that's going to give you that 3.7 volts from your lithium polymer battery, which does mean you have to have a lithium polymer battery plugged in to use this. I think it sometimes works over USB, but you really want to have a battery plugged in to make sure that this works and to give the most power. The ground connection, so that's also this little green wire right here. I just soldered the ground, and this is a magnetic name tag clip that I put on the back here, which makes it a little bit easier to put on clothing. But you can see I just soldered the green wire from ground to the ground on the NeoPixel ring. And then for the signal, I have it connected to the SCL pin up at the top here, which is also a digital pin. So it's digital pin number 2, or number 3 actually, it looks like, on there. And so I just moved it, I just put this little brown wire on here and just connected it there. Now I left a little bit of play, like I didn't make the wiring connections exactly as long as available. I left a little loop of wire here, and that's so that I can move this. So the Circuit Playground, I can actually twist it, like I can bend it up, you know, as far as this if I want. And that's nice because when I'm programming this, I need to be able to plug into the programming port right here. And if I didn't give enough play, you know, if I had just connected it like this, you can see the NeoPixels at the edge here kind of block it. So by giving it a little bit of play, I can tilt it out, program it, and then when I'm done, I just move it back into place. So it gives you that little bit of movement that is helpful. And I use solid core wire so that it stays in place, it doesn't flop around. If you use stranded core wire, it wouldn't, you know, this outer ring would just be kind of flopping around, which you probably don't want. So solid core wiring, leave a little bit of extra play so you can move this around. And then it should fit perfectly. Like I said, there's about a 0.1 inch kind of clearance in between there, which gives you enough room. Oh, and do be careful when you solder to the Circuit Playground. So let's see, let me zoom in a little bit here so we can really see this. Let's see if it focuses. There we go. So you can see this edge right here kind of above my finger. So that's the solder joint where I connected the wire. So notice I don't have the wire sticking out. I actually have it sticking in, and then I just melted a bunch of solder onto there. That's because, again, remember that clearance. So when this comes down, notice how you've just got like a fraction of an inch right there. And if I had that wire sticking out, it might like hit that NeoPixel, or it could touch some of the contacts. You see there's the NeoPixel contact on the side there. That could short that out. That would be bad. So, be careful, and you kind of need to think through. And when I write up a guide on this, I'll put a few more notes on how to deal with that, or just, general strategy for it. But like I said, have your wires facing inward. And then be careful that you don't, because there are some components on the board. You don't want to short out anything metallic on there, so you need kind of a short little play. I bent the wires into a hook shape and then put them into the large holes that Circuit Playground has. And luckily for the SAMD21 Circuit Playground, it's exactly the same format, exactly the same size, at least right now, although who knows, the final board, things could change. So it should be, everything should apply the same to this board here. So let's get started. Like I said, I'm going to dive in and show how to control the NeoPixels on this CircuitPython board. And you could use this to control NeoPixels on any CircuitPython board. And the one trick that you need to know is that you need to download the correct NeoPixel library. So if we go to, did I close? There we go. I'll put a link in the description below so you can find a link to this when this video goes up on YouTube. But this is the Adafruit CircuitPython NeoPixel module or library. And right now it's a simple .py file. This is kind of an older style of library, but it's fine. It works just fine on CircuitPython. And this module is basically just a direct port of the NeoPixel module from MicroPython, but working with CircuitPython's API, because CircuitPython doesn't use the machine API. It uses this board and native IO API. So this is just swapped over to use that. Everything else is the same, like how you initialize it is pretty much the same. How you change the pixel colors, exactly the same as before. And I've done a video on how to use NeoPixels in MicroPython. So take a look at that. That shows you some of the basic usage. But like I said, in this video, here's how you want to do it for CircuitPython. So to make this work, again, just like every other library that we have, go to the Releases tab, and you should see the latest release should have a .mpy file. Or in the future, you might see a .zip file if this turns into a module that has a folder and a certain folder structure like I've talked about in previous videos. If you see a zip file, download the zip file, unzip it, there'll be a directory, and you want to copy that entire directory onto the root of your CircuitPython board. If you only see this .mpy file, just copy this .mpy file onto the root of your CircuitPython board. In Python, a module can be either a file like a .py or a .mpy file, or it can be a folder, a special folder with a bunch of special files inside of it. And just depending on how complex the library is, it may or may not be a single file or a folder there. So let's grab this file, which I've actually already downloaded, and let's put it onto my CircuitPython board. So for this board right now, and I've loaded up with the latest version of the firmware, but like I said, this board, not many people have this yet, so you probably don't have it. But, for example, if you're using the M0 board, make sure to load the latest CircuitPython firmware. I think we're 0.8.4 is the latest version. And you should see the board show up as a drive. In this case, it's called MicroPython, but in the latest versions, it's actually called CircuitPy. So you might see a different named board here. Now, I've already copied this file onto my board, so I've downloaded it and just dragged it over using drag and drop. And this is the other cool thing about this, the Circuit Playground Express board here with that larger flash memory chip. It has more space in its file system. So in a previous video, I kind of showed you had to do some tricks in Mac OS X to copy files over without getting all these weird shadow 4 kilobyte files. I didn't do that here because I have a lot more space, and so I don't really care about those extra shadow files. Like OS X creates these extra files that store bits that say whether a file was downloaded over the internet. Normally it doesn't matter, but when you only have like 64 kilobytes total for all of your Python files, every 4 kilobit file kind of matters, and so you don't want those hidden files to be there. Long story short, for the boards that have this external flash memory, it's going to be a lot easier. You don't need to worry as much. Although if you do run into space issues, like I said, go back to some of the previous videos, and actually in the SAMD21 MicroPython guide, I mentioned this workaround. In Mac OS X only. On Windows, you're okay. It doesn't seem to create these files. But on Mac OS X, you've got to do the copy command with this -x parameter, capital X, to not copy this special file thing. Anyways, long story short, get this .mpy file onto the root of your board, and then that's it. That's all we need to do to control the NeoPixels. So I'm going to open up the board's serial REPL. So let's connect to the serial port, and it shows up this USB modem 115200 baud. And I've connected, and if I press enter, then I get the Python REPL prompt. And to use NeoPixels, it's pretty straightforward in CircuitPython. So first you need to import the board module, and just like all the CircuitPython boards, the board module has all of the pins for the board exposed as high-level objects. So it's kind of nice for Circuit Playground. We're actually exposing the pins with easy-to-use names. So the NeoPixel input pin, which is right here, this first NeoPixel, it's digital pin number 17. We actually call it NeoPixel. So board.NeoPixel is that NeoPixel input pin, which is kind of cool. And there's similarly pins for the microphone, the accelerometer, the slide switch, the left button, the right button, which should make the code a lot cleaner and simpler. And kind of cool in that if we have like more advanced versions of boards in the future with even more sensors and features packed onto them, the CircuitPython firmware will just include that in the board module, and you can just see what's in the board module. You know, you can use this dir command to list everything and get started and you know, just start using it. You don't need to maybe look up and see, okay, digital pin number 17 is the NeoPixel input, and look at the schematic and figure this stuff out. It'll hopefully be a little bit simpler. And again, that's kind of why we wanted to create CircuitPython, to add stuff like this to it. Okay, so I've got the board module imported, and then I want to import the NeoPixel module. So I do this, and this will import that neopixel.mpy module that I loaded. Now in the future, we might actually include this module on these boards, especially the boards that have this external memory. You know, just out of the box, it makes sense for us to include things like the NeoPixel driver and stuff. I mean, even like common drivers for all of our other boards, for all the sensors and things on there. So in the future, maybe you might not even have to copy this file over, but it's good to just understand that ultimately that neopixel.mpy file is what I've copied over, and that's why this import command works. If you get an error, like error cannot, you know, if I try to import a foo module, you see no module named foo, that means there's no file called foo.py or foo.mpy. So go back, check your board file system, make sure that the file is there that you expect to have. Okay, now to create a NeoPixel object, it's exactly like in normal MicroPython. In the NeoPixel module, there's a NeoPixel class. It needs to take in an instance of the pin, and in this case, I'm going to give it the board.NeoPixel pin, and then I need to tell it how many NeoPixels. So there are 10 NeoPixels that I'm going to use here, and that's it. And then I'm also going to plug in real quick. Well, I know, let's try it without plugging in the battery. I think this will work without plugging in the battery, but let's see if it does. Sometimes, because the NeoPixels require a certain, if they're being driven by 3.3 volts of logic, sometimes they work with 5 volts power from USB, sometimes they don't. So in some cases, you really need to plug in the battery to power them. But let's see what happens. Okay, so the NeoPixel object has a fill command, which will set all of the pixels to a color. And so you just pass in a tuple. It's basically 3 values with the red, green, blue component values. So 25500 means full red intensity. Nothing happens until you call neopixel.write, and then I do that, and okay, there we go. We can see it just turned red, so it lit up red. It's not super bright. I think if I plug in the battery, it'll actually probably get a little bit brighter. So let's see. Oh, no, it doesn't. Okay, so it is bright enough. So it looks like this does work just fine off of USB. Like I said, sometimes you need to plug in external power to really get things working. Okay, so that's easy. If I want to turn them off, you know, I can fill them with the color 000 and then write that out, and they turn off. And then if I want to control an individual pixel, I can index into an array from 0 to 9 because there's 10 pixels total. So the first pixel I can set to red. Maybe the second pixel I can set to green. And then the third pixel I'll set to blue, so full blue, and then write these out. And there we go, red, green, blue. And you can kind of see the order that the pixels go on the board like that. So pretty easy and straightforward, nothing too complex about this. But just with those basics, that's all I need to create that arc reactor animation that we saw before. So, you know, with my with the Arduino version of this board that I made earlier, you know, I have this outer ring, and then I have the inner ring of 10 NeoPixels. So for CircuitPython and Circuit Playground here, I'm going to do the same thing. Now, I'm not going to solder this up just because I don't want to make this video too long. So what I'm going to do is I have a little, another ring. This ring's not big enough to put around the Circuit Playground, but it's good enough to just demonstrate. You know, it's the same hardware. And then if later on, I'll solder up this larger ring and then make this a proper Circuit Playground, CircuitPython version of the Arc Reactor, because I really want to be able to say at this Comic-Con, you know, people will see this on your chest and be like, that's really cool. And it's like, yeah, you know, hey, I'm Tony Stark, and I'm sure there will be other Tony Starks at Comic-Con. I would be shocked if I'm the only one. But I will hopefully be the only Tony Stark who has an arc reactor powered by MicroPython and CircuitPython. So that's the one thing I want to be able to say with this. Anyways, let's wire this thing up. So to make this easy, I'm just going to use alligator clips, or these little alligator wires. These are super handy. Let's zoom out a bit so we get a little bit more of the workspace visible. And then this is very easy to wire up. I'm going to wire it up exactly how I have my the non-CircuitPython version of this wired. So let's go from, let's see, we'll do the red wire to the VBAT input. So that's the battery output on here. That's the nice thing about Circuit Playground, any of the Circuit Playground boards. They have these nice wide holes, which are perfect for alligator clips, so I don't even need to solder things onto here. Now for this little pixel ring, I have the power lead that I need to connect, so I'll wire that up. And then let's do ground. So there's a ground on the side here, the G and D pin, okay. And I'll hook that up here. And you do want to be careful when you're wiring things up. You know, don't let your power and ground leads touch each other. So like, you know, if I can, I'll try to like move these onto opposite sides of each other so that, you know, there's no chance that they'll short out, because you probably won't fry anything, but you will get very erratic behavior and your board will probably reset because it's pulling a lot of power. Okay, the last thing is the SCL, or digital input number 3, or digital input output number 3. I'm going to connect to this green wire, which is the input of this NeoPixel strand, or well, ring rather. So here's the ring, and I've just hooked up the VBAT to the power input of the NeoPixel ring, the ground to the ground of the NeoPixel ring, and then the SCL, or digital pin number 3, to the input of the NeoPixel ring. Now, unfortunately, you might be wondering, like, could I hook up the input of this external ring to the output, the very last pixel on Circuit Playground, which would mean then that you would just extend the ring of pixels so that this would look like one giant ring, or one giant strip of pixels. Unfortunately, you can't right now. I think it's someone that's suggested it, and I don't think it's in the current designs, but there is no output that you can grab. You know, you would want to grab the output of the last pixel, but you'd have to solder onto the tiny little kind of side connectors on that last pixel. Don't try that. So what you can do is just connect your NeoPixels to any of the free digital inputs or outputs on Circuit Playground, and then you'll just have 2 NeoPixel strips. So you'll have your internal strip, your inner ring, and then your outer ring as 2 different strips, and you just need to know to set them both to, you know, different colors and things like that to make it all work. So okay, so let's play around with lighting this up. First of all, let's just make sure that this thing works, and I'm going to plug in a battery now because I'm using that VBAT line. It's not going to really get any power until I plug in a battery. So let's plug in this little lithium polymer battery. Oops, come on, plug in. There we go. So I plug that in, and now let's make a new NeoPixel object. So np2 equals NeoPixel.NeoPixel, and the input pin that this is plugged into, or the digital output on Circuit Playground, this is the board.scl pin. It's the SCL pin that it's connected to. And I noticed we don't have the digital pins listed right now. I think that's just a bug right now. Like I said, this is all in development for the Circuit Playground board, so there's probably going to be in the future a D3 pin that you might be able to use instead of this. And then there are 16 pixels in this ring, so I'll do that. And then let's just make sure that we can light them up, that I got the wiring correct. So let's see if we can set them red, and np2 not right. So I do that, and there we go, it lights up red. So that's cool. And then, you know, if I want to control that inner ring, that's the np object here. So I can fill this up, and let's set this to a blue color, and then np.right. And there we go, so we got blue and then red. So you can imagine, you know, if I had this as kind of this configuration, maybe the outer ring would be red and the inner ring would be blue. Which would be kind of cool for this. And that's kind of one neat thing, is I want to play with different colors. Like I said, you know, the arc reactor is it's all just a bluish cyan color. You know, why not? If I have the ability, I'm gonna make mine red. I'm gonna make mine, you know, green, blue, pink, whatever color. Make it rainbow colors. So I'm gonna have some fun with this. Okay, so let's start writing some code in an external file now. Let's open up the CircuitPython board. So I'm going to open up this the MicroPython drive, which is actually the CircuitPython board, and I'm going to actually write some files directly onto that board. Now, before I do that, I'm going to reconnect to the serial REPL. I'm going to press Control D. D as in dog. That does a soft reboot, and notice now this auto reset is on. So auto soft reset is on. So now anytime that I save a file to the drive on this CircuitPython board, it's going to reset and just rerun whatever I put into that file. Well, specifically, it's going to rerun the main.py or the boot.py file. So if I make a file called main.py, and let's just have it print hello world, and then if I save this as main.py on the board, then we should see in a moment here. So notice this. This is the serial REPL. I just have it open to see the output. I'm not actually touching anything, because if I actually press something, it will stop this auto reset logic. But just press Control D to do the soft reboot to rerun it. But notice it said, okay, it noticed that I saved that file. The file changed, and it ran it, and then here's the output from it. It says hello world. So this is cool. This is a good way to have a really fast development cycle with CircuitPython. And I think we've shown this off a few times. But you know, basically, if you can open a file that that is on a USB drive and edit it, then you can run Python code interactively. You don't have to use a fancy editor. You could use Notepad or whatever. I'm using the Atom text editor, but I don't have to use that. I could use anything for this. So okay, so let's put in some of this NeoPixel code again. So let's import the board module. Let's import the NeoPixel library, and then let's just create that inner and outer ring again. So we'll say my inner ring equals the NeoPixel.NeoPixel, and that one is connected to the board.NeoPixel pin, and that one is 10 NeoPixels large. And then let's make the outer ring. This is the NeoPixel module, and it's the board.scl pin, and it's 16 pixels large. Okay, and then let's just turn them off to start with. So we'll say inner.fill with 0, 0, 0, and then outer.fill with 0, 0, 0. And then I want to write to both of those, inner.write and outer.write. So let's do that. I'm just going to press basically the Apple S, or here I'll just show you file save. I'll press file save, and then in a second, hey, they just turned off. Like it noticed this file changed, it ran the code, and the code ran to turn everything off. So that's pretty cool, and it's very fast, easy way to do this kind of development. Okay, so one thing I wanted to do real fast though, because I think this is going to be a common thing for a lot of people. Notice I have these two separate strips, but I really just want to control all of the pixels at once. So wouldn't it be nice if I had a concept of like a NeoPixel chain, something where I could give it multiple NeoPixel objects, and then it would just treat them all as one large NeoPixel object. And the cool thing is, with Python, I can do that really easily. I can make an object that looks like the NeoPixel object, that has the same kind of getter and setter functions, and that, that looks like one, but takes in a bunch of NeoPixels internally and then uses those to set themselves. And I've done this ahead of time. I'm going to save some time. I'm going to open up the file that I created ahead of time. Let's see. This was from my downloads. Now I did it. Let me go back to downloads here. I did it here. There we go. CircuitPython. And then let's go to this testing folder. So I made a NeoPixel chain class. And I'm thinking I'll put this probably in our NeoPixel module. But for now, I'll put this up on a gist on GitHub, and there'll be a link in the description when this goes up on GitHub. But I basically just made a class that lets me pass in a bunch of NeoPixel objects, and then it implements all the same functions as the NeoPixel class. So it has a fill function, a write function, a get and a set function. But the cool thing is, it makes a bunch of individual strips look like one long strip. So I can fill them all, I can index into them, and it figures out exactly which strip I want to set for this. So this will be super handy. Oh, and I just noticed someone had a question, does this module support the RGBW pixels? Yeah, this module does. The CircuitPython version of this code, we updated it to support the RGBW pixels. The way you make those work is there's this bits per pixel or bytes per pixel parameter. Just pass in, by default it expects 3, but pass in 4, and then that'll let you pass an extra byte, which is usually like your white pixel for the RGBW pixels. Anyways though, so this NeoPixel chain .py, I'm going to copy this over to the board because this is, I can import this as a library or as a module, and I could make this a .mpy file, but I don't have to. So I'm going to grab this file. If I go back to my downloads, Arc Reactor, and if I grab this chain, and I'm going to drag it onto the board here. Okay, so now I have this chain class available. And I'll show you how to use this. It's really simple. I tried to make it very, very easy. Basically, I need to import it. So I need to import NeoPixel chain. And then I need to construct a couple NeoPixel objects. And you can have any number of NeoPixel objects. You just pass in all of your NeoPixel objects to the constructor of this. Then I need to create a chain. And so this equals NeoPixel chain dot NeoPixel chain. And here you just pass in every single NeoPixel object that you want to tie together, and it will do them in order, which it doesn't really matter, but if the order does matter to you for some reason, you know, so this inner one will be the first 10 pixels in this chain, and then I just put a comma and I just put the next one, and I can just put as many as I want here, just, you know, using commas. If you're kind of curious, this uses a syntax in Python that looks like this. When you use this star operator, this just tells Python, I expect any number of positional arguments, and it will just give you a list of all the positional arguments that you can just loop through like I do right here. So really, this is what I love about Python. You can do all kinds of things like variable arguments super easily, and it's, you know, makes a lot of sense. And you can do this stuff in C and C++ actually, but you have to use all these weird macros and funky stuff. Okay, so anyways, so I'm going to pass in the inner and the outer. So my first 10 NeoPixels will be the inner ring, and then my next 16 pixels will be the outer ring. And so there'll be 26 pixels total for this. And actually, if you want, so well, here now, let's just to show how this works now. So the chain object is what I want to control now. So I don't even need to control, you know, my outer and my inner one individually. It's really just the chain object. And then let's set this red again, just to make sure I can see everything. And then I'm also going to just print out, you know, total pixels, and we'll do .format. And if you want to get the number of NeoPixels in a NeoPixel object, or this chain object also, there's a .n parameter, which is number of pixels. It's just kind of how it was implemented. I would have picked a better name, but I think this is fine for this. Okay, so I'll save that. And hey, look, everything just turned red. And if I go to my serial terminal, I should hopefully see, there we go, total pixels 26. So that's cool. And then just to show that this really does let you index into those pixels, you know, let's set chain, you know, pixel 3. So that should be in the inner ring of pixels. Let's set that to red. And then let's set pixel, how about 12? That should be the very first pixel on the outer ring. Because the last pixel on the inner ring, oh no, sorry, pixel number 10 rather would be the very first pixel on the outer ring. Let's set that to green, and then let's set the very last pixel, which should be 25, because it's 0 indexed. Let's set that to blue, 250, whoops, not 3, there we go, 255, okay. So I do that, and I save it, and there we go. So yeah, so I've got, you know, a few pixels down is red, because remember, it's pixel number, it's the 4th pixel down actually that I'm using. And then right here, the very first pixel is green, and then it wraps all the way around to the end. The last pixel is blue right there. So that's kind of cool. You know, this chain object looks like a single strip of NeoPixels, but it's really made up of a couple distinct NeoPixel strips or rings or matrices or whatever you want to use. You can put them together and make this work. Okay, cool. So now let's just do this quick little animation. So I did like a breathing animation where it kind of, the colors fade between like a one color and a second color, and it does it kind of based on time. And I'll show you how I did that. So it's really pretty straightforward. And I've done this a bunch of times actually, but just to make this a little more explicit, so let's just put some comments in here. We'll say this is the setup code. So we'll say create the inner and outer NeoPixel rings, and then set up chain of NeoPixel rings as single entity. And then let's just say we'll turn off all the pixels in the chain. It's usually a smart thing to do at the start. Okay, I don't need to print these out anymore. And then let's do a main loop. So while true, this is just going to run forever, basically. And then it's always smart in your main loop, especially with CircuitPython. You want to import the time module. And actually, yeah, let's import time. And always put in a small delay. Because in some cases, we need to give some time back so that things like the USB file transfer processing can happen. And we might have fixed this so that it happens in the background all the time, no matter what. But it never hurts to give a little bit of delay here. It's kind of like in your operating system, it needs to be told, hey, my program's done. Here's some free time, or do whatever you need to do in the background, like finish whatever processing. Like on the ESP8266, sometimes you need to do this also if you're processing Wi-Fi and stuff like that. So we'll just add this just to make sure that I don't kind of brick my board or make it so I can't copy files over. You aren't really bricking your board when this happens. If you get into a main loop like this, you're just gonna have to go into the serial REPL and press Control-C to stop it, and then you can go back and start editing things on your board again. Anyway, so let's do that, and then let's just save this so that my main loop should be running. Okay, so now it's running, and okay, so to animate all these pixels, what I'm going to do, I've done this a bunch of times, I'm going to use a sine wave, because basically I want to go from one color smoothly down to another color, just over and over, just over time. I just want to go, color 1, maybe cyan, all the way down to color 2, my red color, and then smoothly in between those, just over and over, the way a sine wave works. The cool thing about a sine wave is it's a function based on time. So if I give this function my time in seconds, it's going to give me this smoothly changing value that goes from 1 to -1, and then it will go smoothly in between all those values in a nice curve. So it's a great thing when you're like animating things that you want to make look natural. Sine waves you're going to use everywhere. And there's a nice little formula for them where you can kind of control how often, the frequency, how fast they go from one extreme to the other extreme. And so once I have a value that goes from 1 to -1 over and over, I can use linear interpolation, which I've shown this in a bunch of other videos, to basically take that value that goes from 1 to -1 and turn it into a value that goes proportionally within another range. So a value that goes from maybe 0 to 255, like the range of colors for the red, green, blue component. So that way, using linear interpolation, it's just a formula. I plug in the output of my sine wave, which goes from 1 to -1, and then I'll linearly interpolate so that, if my value that I get from my sine function is 0, which is exactly halfway between -1 and 1, if I get a value of 0, then let's say I want to linearly interpolate that into the range of 0 to 255, that would give me a value of 128, like right in the middle of that 0 to 255 range. And then likewise, if I get a value of -1 from my sine function, it'll give me one of the extremes, like 0, from my range of 0 to 255. So it's a way to map the output of one function to another function that expects a different range of values, and it makes a linear relationship between that, hence the name linear interpolation, where it's just a one-to-one mapping, so that if I'm exactly halfway in between my input range, then my output value will be exactly halfway between the range of output values for this. So that's what I'm going to do here. I'm just going to implement this. So usually I start by implementing the linear interpolation function. So I usually call this lerp. That's just what I learned long ago when I was doing graphics coding. Because there are different versions. There's like an exponential interpolation. There's like cubic interpolation, which just give you like different curves of smoothness. It's something cool to play with. But we'll call this lerp. It takes in an input value x and then the range x0, x1. And then it also needs to take in your output range, your y0 and y1 range for this. And then I'm literally just going to copy right out of Wikipedia this formula right here, because that's all I need to do is just return that value exactly as Wikipedia shows it. So let me just make sure that you can see this here. Oops, let me drag this over a little bit. Come on. So yeah, we'll move that over. So I want to see basically this formula right here. So I'm just going to exactly return this as is. So we'll say y0 plus x minus x0 times y1 minus y0 divided by x1 minus x0. I still haven't memorized this, which is sad. This is like the easiest equation. It is fun to work through this and actually kind of think about, because what you're basically doing is looking at like what's the magnitude of your x range and then what's the magnitude of your y range, and using that to create a scale value. And then you're just looking at what is your position within that x range, and then multiplying it by that scalar, and then offsetting it by your start position, effectively, this y0 here. So that's really what's happening. But if you kind of step through each of these operations, it makes a little more intuitive sense, and it's kind of interesting to do. Okay, so I've got my linear interpolation function here, and then my sine wave function is the next thing that I want to do. Now, to power this sine wave function, so right here, this kind of talks about, here's your general form of a sine wave equation. So A is your amplitude, that's how big that range of values is. If you just use a value of 1, then you'll get outputs that range from 1 to -1, which is fine. Because in my case, since I'm using linear interpolation, I really don't care what that range of output values is, because I'm just going to tell my linear interpolation function exactly what that range is. So I'm going to keep A equal to 1, which means I'll have nothing there. But F is your, so then you have 2 times pi, and then times F. And F is your frequency, or the number of oscillations, the number of times it goes up, down, and back up again in a second, or in a period of time, because it doesn't have to be seconds that you're using for this. I'm just going to happen to use seconds because it makes more sense to me intuitively. So if I use a frequency of 2, that means it's going to oscillate twice per second. So it's going to go from 1 to -1 and back up to 1 twice a second. And it starts at 0 and goes up to 1, and then it goes down to 0, and then down to -1, and then back up to 0. Or if you use a cosine function, then it's offset in a slightly different phase for it. Doesn't really matter. It's going to change. The frequency controls how often it goes from 1 to -1 effectively for this. Now you can add this last little thing here, this which I forget which Greek symbol this is, but this is your phase, which is just kind of, think of it like an offset of the starting position. I'm not going to use it because I don't really care what the phase is. If I had different sine waves with different phases, then they would be at different points along their curve at the same point in time. So like you can actually see in this little graph here, this blue dotted line is a different phase from the red dotted line because it's just offset in time. But it's the same amplitude, it's the same height, and it's the same frequency. It oscillates the same number of times. It's just the phase is different for this. So, but I don't need to use that. I really just need to use a simple form of this sine wave equation, which is literally just sine of 2 times pi times frequency times my current point in time for this. So, okay, so let's first get my current point in time. And in CircuitPython, you want to use the time.monotonic function. And basically this function will give you the time in seconds, but it's not like your wall clock time. It's just a timer that's always increasing once a second. And it's actually a floating point value, so you get like millisecond kind of accuracy with this. So this is useful because I don't care, that it's like 4:45 p.m. I just care that it's, X number of seconds, and that 2 seconds from now, it's going to be X plus 2 seconds. This value is going to increase by 2. I just care that it's a value that increases over time. And that's exactly what this time.monotonic function does. In MicroPython, they don't have the monotonic function implemented. You want to use in the time module, there's ticks, T-I-C-K-S, ticks underscore ms. You can get a millisecond tick count, which is effectively the same as this. But the nice thing is, in proper desktop Python, the time module has this monotonic function, and so we figured, well, let's add that to CircuitPython so that it's the same as desktop Python. Okay, so that's my current time, and then let's get this x value using that sine function. And so to do that, I need to import the math module. So we'll import math, and then I'm just going to do math.sine. and then 2 times math.pi. Luckily in Python they already give you that pi constant, times my frequency. So let's just say configuration up here. So let's say frequency, and let's do twice a second. We'll start with that. Okay, so times that frequency value times my current time in seconds. Okay, so that's going to give me an x value, and this x is going to range, it's going to go between 1 and -1. So it'll smoothly, you know, go between those values just based on that sine wave curve that we saw before. So then using that x value, what I want to do is feed that into my linear interpolation, and then use that to get my color values. So let's get my red color value, and I need to know, I want to have like a starting color, I'll call this color A, and an ending color, a color B. These are the two colors that I want to oscillate between effectively. So we'll say color A equals, let's just set this to red, and then color B, let's set this to blue. Okay, so now I need to compute the red, green, blue color component values individually for this. So I'm going to do, let's lerp, we're going to call my linear interpolation function. I'm going to give it that x value, that's the output of my sine wave. And I need to tell it the range that that x value goes between. And so that goes from -1 to +1. And then I need to give the output range. The value that I want to get should fall within this range. And this should be 0 to 255. So that's, oh, well, actually, no. This should be my input color, my starting color, the first component of it. So I want to get that color. And then the output, or the final value, oops, uh-oh, I pressed the wrong key there. I want to get my second color, my color B. So if I had 0 and 255, this would just map between like off and on completely. So I wouldn't get like the color I expected right here. You know, I need to look up and see what is my starting color. And so that's what one of the limits of my linear interpolation output would be. And then what is my ending color? That is the final output value. And then the linear interpolation is going to pick the color within, or pick the value that falls within that range of colors, depending on where my input sine wave value falls. So I'm going to do the exact same thing for the green and blue components. So we'll just say red, green, and blue. I'm just going to copy these, and we'll say green, and then we'll say blue. And then for this, I just need to change my color, the index, into these color values, because you know, color 0 is this 255, that's my red component. Color 1 is the green component, and then color 2 is the blue component right here. Okay, so we're pretty close. So now let's fill my chain with the color that I just computed. Now, one little thing, the output of this linear interpolation function is going to be a floating point value. I can't use a floating point value to set the colors. I have to convert them to integer values. So you can just use the int function in Python to do that. So if I send the integer value of my red, my green, and then the integer value of my blue, I'm going to pass that to fill. And then I'm just going to make sure I get the right number of parentheses. Oh yeah, it looks like I did. That's a nice thing of using an editor like this. It kind of tells me if I have all the parentheses set correctly. Okay, fill, and then I want to make sure to call write, because that will actually light up the NeoPixels. And then let's run it. So I'm going to hit save, and let's see if this works. Hey, check that out. So you can see it's going from red to blue, back to red. And it's pulsing. It's doing this nice cycle, very smoothly going between those values, because it's using that sine wave that, you know, very smoothly goes between the values, but it's using the output of that sine wave to interpolate which color it should use. And if I change this frequency, I can make it really fast, like let's do 5 times a second. So now you can see it's like, whoa, this is the hyperactive arc reactor. Or I can make this a smaller value, like let's say 0.25. So this is, you know, it's going to take 2 seconds to change, to do one full cycle effectively. So you can see this is nice and slow. So it goes in between the values. You know, how about something like 0.67? That might be a more kind of, yeah, there we go. That's kind of nice. You know, it gives this like nice kind of breathing kind of animation to it. So that's cool. Then if I want to change the colors, for example, if I want to go from, let's say, cyan, which is full green and full blue, to just full blue, I can do that. So if I save this, so now you can see it goes from cyan to blue, and the cyan kind of looks a little greenish on the camera, but you can see this is, you know, pretty cool, kind of nice I don't know, nuclear reactor fusion-y kind of looking thing. But like I said, this is fun in that now if I want to change the color, all I have to do is just change these color variables. And I could actually write code later, maybe in a later video I'll do that, where if I press the buttons, I could make a list of colors and have it just pick the next color in the list so that I could cycle through colors with this animation here. So that's pretty cool. So that's all I wanted to show in this video. I'll wrap it up. It's starting to run a little bit long. And basically, like I said, I wanted to show how to use NeoPixels with CircuitPython. You want to use this little CircuitPython NeoPixel library because this is using the CircuitPython API, which is slightly different from the MicroPython API in this case. So use this library and you'll be all set and ready to use NeoPixels. And then in the future, I'm sure I'll do some more videos on this Arc Reactor project. So like I said, I built it using the classic Circuit Playground, but now I'm going to rebuild it using the fancy CircuitPython Circuit Playground because I want to be the only Tony Stark that has an Arc Reactor that's running Python code. I think that'll be pretty fun and unique for cosplay. So if there are any questions, throw them into the chat. Oh, someone's going to ask, if there was a class that combines multiple NeoPixel strips. And yes, now there is a class that does that. And like I said, I'll put this up as a gist on GitHub. It's a pretty straightforward class, and I've kind of commented it, so if you're curious how it works. I mean, basically, you just take a collection of NeoPixel strips, and then you map those into a large global index. So, if I have this strip of 10 pixels and 16 pixels, now I have a global 26 pixel long strip. And then when someone says, okay, set pixel number 23 to red, I need to figure out, okay, pixel 23 actually falls within the second strip, and it's, index number, I don't know, it'd be like index number 13 or something onto there that I'd want. So you have to do a little bit of math inside of here to figure out where your pixels will fall. But it's not too complex, and you can kind of see how this works in the comments here. So, okay, cool. I'll wrap this up then. So let's see, we'll jump back to the main view. Let's see, we'll turn that off and go back here. So yeah, again, this is Tony from Adafruit showing off NeoPixels and CircuitPython. If you like this stuff, then check out youtube.com/Adafruit. You'll see this video and all kinds of other fun project videos up there. And check out twitch.tv/Adafruit. That's where I like to stream things live. You can watch these kind of as I go with them. And we're doing all kinds of fun CircuitPython stuff. And stay tuned. You'll see a lot more fun project videos. And hit the like, the comment, the subscribe. Let us know that this is good stuff and good content, and we'll keep making it. So until next time, I'll see you later. It's Tony from Adafruit. Thanks for watching.